So it's recording. Okay, so I would like to basically try to explain stage 2 of our CTF challenge. So in stage 1, you are being tasked to actually just watch a movie, and in that movie you can make use of stereography to actually find the solution to the flag, or like to the flag for the first stage, which as of now the movie is down, so the answer is actually just Daddy Allen. But basically using that particular flag, you'll be able to decrypt with AES CBC the file for stage 2. So proceeding, I would like to explain more about stage 2, which is actually a more interesting. So congratulations on getting past your first stage. So that yeah. So for stage 2, you'll be tasked to crack an Enigma machine, which is something that was made by the Germans during World War II to actually encrypt and decrypt their messages so that the Allied powers would not be able to see, or not be able to read what was actually being passed, military intelligence and so on and so forth. So you are an MI6 research, and you're a futuristic person that came to existence, blah 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 blah, trying to like basically use a PC to actually solve to crack the Enigma machine. And you learn that the Germans have actually now been able to use a character set of 94 characters, which is the number of printable characters. So let's Alan Turing as will be helping you today to actually solve this Enigma machine. So I'll just go through. I won't be going through too in depth onto how the solution is done technically, in the sense of like the coding and so on and so forth. You can look at that in our proposed solution if you do not really wish to crack it. But we have implemented the solution in Rust, which basically would contain what I'm gonna tell you, and like what are the tips on how to crack it. So I'll just go through briefly like a whole guide as to like this whole Enigma machine CTF. So what is an Enigma machine is basically used to encrypt and decrypt encode like coded messages during the World War II era. So the cool thing about the Enigma machine is that when you actually type in AA, you do not get back a one to one. Actually, yeah, you don't get back one to one. It's actually polyalphabetic, so you get back E and J instead. So how is this done? Well, it's actually a basic like substitution cipher, but instead of, if you take a look at how an Enigma machine works, it's rather interesting because what happens is that it contains a plug port, and then it contains the like scrambler section. So let's explain. So let's say a person wants to press E. What happens is that it'll go through the plug board and then go through wiring to another value, for this case is J, and then it will goes into a stator, and then from the stator it will basically go through a wheel, three wheels and a reflector, and back the same wheel set back into the stator, and then back to the plug board, and then give you the output. But remember that when you write AA, right, you actually get E and J. So how does it work, right? So every time you press a button, what happens is that the third wheel will actually spin, and that is your fast wheel. So in the Enigma machine, you have three wheels. This is the fast wheel, this is the medium wheel, and this is the slow wheel. So every time you press a button, every time you press a key, this fast wheel will click by one. And after spinning round for 96 iterations, what happens is that the mid wheel, there's a notch that will mechanical notch in real life, that will actually click one onto the medium, and the medium will actually flip by one. So after the 96 for the medium, then you will actually flip the slow by one. So that's how it essentially works. So you can see why it gets a bit complicated. So AA here would not match back to the same like EE, you'll match to E and J, for example. So this is why it's challenging to crack the Enigma machine. So the Enigma machine in real life, it actually looks like this. So the Enigma machine back then was just 26 characters, which is A to Z. So this is what you see here. But the Enigma machine that we'll be trying to crack in the capture the flag here is using 96 characters. So here's how it works. So there's two parts, right? The plug board and the scrambler. So for the plug board, you have wires that will connect from, let's say for this case is A, and then you'll connect to, oh sorry, wrong. You will connect it to J. So that's how it works in the actual Enigma machine implementation. So every morning, the Germans will actually configure the Enigma to that particular day's Enigma plug board settings based on their, like, based on what they have determined, or like what they have discussed and agreed upon that day. So that makes the Allied extremely difficult. The Allied powers had a lot of difficulty trying to like crack this Enigma machine, trying to determine what is the plug board setting for that day, and if they are not able to actually solve it within the day, they are not able to get the any messages for that day, and or at least find it very difficult to find it, and most of their information or intel will be outdated. So that's the difficulty here. So when you can take a look at the plug board, let's take a look at the plug board in fact. So for the plug board, right, you in the old times, the Germans actually only used 10 wires, which essentially means that they will connect up to 20 letters, and you will have 6 letters left that are not connected. So those letters that are not connected, right, they just get mapped back to itself. So let's say you press, in this case, T. What happens is that on the first, like, plug board like input, right, it will go into T, and then it will come back out as T out to the scrambler. So that's basically how it works. So if anything with like A and O, then I keep going back to O, A and J, right? So A and J, then obviously you just basically just wire it to J. So if you look at figure 3, this is basically how the internals works. I won't be going too in depth into it. So like this, if you want, you can just take a read about it. So figure 4 shows the actual rotor internal wiring. So the rotor basically has like actual like wiring that's connected to the order of the rotors. So that helps with the figuring out, like, I mean, not really figuring out, but like just for that particular rotor's configuration of that Enigma machine. Okay, so so I realized something. So I didn't really explain to you how the Enigma machine was worked for the Nazis. So they basically like basically key in, I said, like, they key in the letter and then they get back an output. So from that output, what happens is that a second person will actually like write out, like, maybe if he gets maybe based on this case, right, he will get back E and J. So the person who actually, this particular E and J will be passed over to the other guy, the party that's the receiving party, and the receiving party will just type E and J back into their machine, and you just reverse, right, you'll go back into the machine, and you'll output back an A and A. So that's the cool thing about the Enigma machine, and that's how they get the message. So this is just more things about the Enigma machine. So this is like the Enigma machine's biggest weakness. So what is its biggest weakness is that basically you will never be able to like get back its so let me just show you. So for example, this particular value here, right? So over here, when you have if you can never map back to the same character. So that's basically what it means. So the Enigma machine's biggest flaw is that it will never be able to map back like R to R, A to A, but it will, whenever this happens, means that like this particular configuration is wrong. So we will actually use this to actually minimize the number of combinations that we should try. So this is just some more information about how the Enigma machine's weaknesses are, to give you some ideas on how you could possibly crack the Enigma machine. But I will just explain our proposed solution as to like how we actually solved it. But it's also all based on like our research onto the weaknesses of the Enigma machine. So that's the blockboard configurations. You can have a read about it. And this is your to-do. So your to-do is basically you receive this particular ciphertext, and this is basically the known plain text that you've got, which contains the weather report, as well as the the final like the tail message of any like German message. So this is very realistic or like very close to real life, as when the British were trying to crack this, they had information that the known plain text is basically just weather the weather reports, and also the ending, which is this. Yeah, so this is the plain text. Sorry, this is the ciphertext that you'll be getting, and from here you can try to make use of the plain text to try to minimize your search. So that will basically help you. And yeah, so let's move on. Let's see what I can help you with. So best router configurations. Okay, so basically this part here is basically just me explain to you how this router configuration, how to actually solve the router configuration and the plug board, at least for our proposed solution. Yeah. Okay, so it's recording. So I'll be explaining to you how you actually solve the router configurations, or how you actually try to guess or crack the router configurations. So if you remember that our Enigma machine would have three routers, then we have a stator, and we have a reflector, and we also have a plug board, right? So I'll just how do I draw the plug board? I'll just do this, okay? So the thing to notice here is that how, at least, okay, so all this solution is how we propose solving this Enigma machine, but because this is exactly what we use to crack it with our implementation. So the first thing that we notice is that the plug board, right, the Germans here in this case have only used 10 wires to wire up their plug boards. That is a huge, or like they, or even just so that they, as long as they don't use up all of the available like plug boards, right, or plugs, that is a huge like flaw on their side, because what it means is that we can make use of this as our Achilles heels. So how it works is that it means that we have many of these like inputs that are going to be mapped back to, that are going to be independent of the plug boards, because it will map back to itself, right? So let's say like this particular thing here, wires are only connected to maybe like that, right? So this particular thing here will go through, come out, and then it will basically just come out from here. It doesn't, it is not affected by the plug board, because the plug board doesn't actually have wires connected to this particular hole. So a lot of these holes will not be actually plugged, and that means that we can actually try to brute force the rotors without even caring about the plug board first. Yeah, so that's how we went about to start cracking the Enigma machine. We start cracking with the stator, the rotors, and knowing that the plug boards, most of the plug boards or the plugs are not actually filled. So with this information equipped, we can try to solve the rotor. But before I go about to solve the rotor, I would like to explain how double stepping works. This We have checked that for this CTF, technically you don't need to implement double stepping. But initially we did implement it with double stepping, but we realized that it didn't really affect our solution. You are still able to solve it. Although you don't get back the exact plain text, you can just look at the message, and it's pretty obvious what that particular letter is. So you can just make use of your analysis of the English language, or like the German language. So I'll just explain how double stepping works. So this is the fast, this is the medium, and this is the slow rotor. So remember that every time you press a button on a key, you will rotate this by one, and when this hits the notch, then the medium rotor will click, and when the medium rotor hits a notch, then the slow rotor will click by one. So what is double stepping? So double stepping occurs when your mid rotor, right, is already in a notch, and already in the notch. So let me just write this down. Add notch. So I'll just put it as add notch. And then your fast rotor clicks. So what happens is that on click, right, this fast rotor, although it is not in a notch, there is a mechanical flaw in the Enigma machine. So when this particular fast rotor, as long as your medium rotor is at the notch, and your fast rotor is to step by one, your medium rotor at the same time will actually step by one. So think about the applications for the slow rotor. If the medium rotor is is already at notch, right? So it's clicking, it'll go by one, then at the same time, your slow rotor will also click by one. So that is basically how double stepping works. Okay, So that's basically the brief explanation of double stepping. You can try to implement that, but I will not be going too in depth into it. So right now we will try to we now that I've explained that, we will basically explain how we will crack this. So basically what to do. We know this, and we're looking at this now, right? So it's actually quite simple. Just brute force all the rotor configurations, all the starting rotor configurations. Basically you choose the starting rotor configuration is your key, right? Your key is gonna be your key to actually solving the first part of the Enigma machine. So using this particular starting rotor configuration, what you do is that you choose a rotor configuration, and then you basically just decrypt it, ignoring any wires connected to the plug board, decrypt it with the ciphertext given to you, and you will do a fitness test. So what is fitness test? So like, remember that you are given, so fitness test is like, for example, let's say we have a ciphertext here, right? And the ciphertext is like some ciphertext. So the ciphertext, when you decrypt it with the Enigma machine, you will get back roughly like so-called the plain text with like double quotations. So it's not exactly the true plain text, but remember that I was saying that most of the things will be mapped back to itself. So what it means is that you will be essentially getting back like a high possibility of getting back a value that's not affected by the plugboard, and that means that if you compare this plain text with the known plain text that you have, you can sort of determine the best or like the closest plain text, like with double quotations, the plain text that you have found, uh, the closest and the best fitting rotor configuration. So you will brute force all the rotor configurations and do this fitness test, so by basically finding how accurate your found plain text is to the known plain text, and then that will help you determine the rotor configuration that is most likely your solution. For our CTF case, it is very obvious. Like the fitness value, basically the ratio is very very significant, so you will have no problems using this method. The second, so yeah, but things to take note when creating this Enigma machine, you have to notice that the rotors, right, will be spinning. So because the rotor is spinning, it's very hard to basically do a hash map if you are doing the technical implementation. Instead of thinking of it as a hash map, you should probably think of it as more of a relative positioning. So like for example, you can imagine like there's a stator for every, like before every single rotor spin, and that allows you to basically map like one position to one position. So every time you map through a stator, and then you go through this particular rotors, everything, you come out, then you have to map it back into the status, like relative to the stator. So yeah, so basically you have to think of it more of like think of it more mechanically than to use, oh, I'm so bad at drawing. Think of it more mechanically than to make use of like what you know in terms of like computer science, because back then it's all wiring, right? So we want to make it easier. So go through, and then this is like, I don't know, I'll just I'll try my best. So to draw, this is the stator. Go through, and then you can basically, for example, like map like 1 2 3 4 5 6 7 8 in a spinning fashion, right? So every time the rotor spins, right, what happens is that the numbers will change. So sometimes this number here could be 12, but you want to basically make use of the stator. So the stator, you want it to be fixed. You want the stator to be fixed in like this, like blah 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 to 20, I don't know, 96. So you want the stator to be fixed. The reason is because every time you go through, right, from 12, this particular thing will have its own like mapping from 12 to maybe like 3, and then it comes out, but you want to map it back into the original stator. So you want to duplicate the stator so that the stator will become your like relative point, so that, because your rotor is going to be spinning, and that is the one that has like, there's dynamic positioning. So like you don't really want to make use of like just hash 1 to 1, because your wiring will become very very complicated. Like you would not be able, I think when you try to implement it, you realize how difficult it is. So when you realize that, then this will make more sense when I tell you like you have to make use of like imagining there's a fixed data here, so every time you come out you have to map it back onto the data. So one way is you can actually like take maybe like 1, and then you go and find this position, you just add 12. Like if you know that the rotor has spin by 12, then you just add 12. Then by the time it comes out, right, you just minus 12, so that you'll get back, you go back to its original position. So I know this will be very, this part is very confusing. But when you guys try to implement the stator and the rotor, right, this is actually one way to solve it, and I think it'll make more sense once you try. So basically add 12, then you get the ready position of the rotor. Then after you map ready, right, then you get back the ready position of the stator. So you have to minus 12 again. Yeah. So I'm just gonna let you guys like sit on this. Okay, so I'm gonna move on to the last thing. So the last part of our guide is basically just how to crack the plug board, right? So to crack a plug board is also very simple. So like you have already cracked the you by this time I think you will have already cracked the rotor configuration. So you can make use of the rotor configuration, just stick to it, don't change it. Then from there, right, you just basically do the same thing, just brute force all the possible like wiring, and from there you also do a fitness test. So you should possibly do this, and then you will get back like from here, then you'll get the best like fitting wire. So like basically what you have to do is, before you even do anything, right, you have to make use of the plain text, the known plain text that's given to you. So maybe what we have done is we've used the ciphertext, right? So let's say we have 10 wires that we want to connect. So the first thing is first is that we know that the ciphertext will be mapped to a particular letter. So this particular ciphertext will be mapped to this particular letter. At least we think that it's going to be mapped to the particular letter, but because if you look at the Enigma machine, you realize that sometimes it's actually not mapped back to not mapped back to its the actual like value. So you can't just basically just choose like, oh, if this is mapped to A is mapped to W, you can just say that A is mapped to W. That's something that we found out the hard way when we were trying to crack this. So how it works is that you want to find the 10 wire configurations that give you the best way, or like the best fitness for this Enigma machine that allows you to actually crack the Enigma machine. So let's say we have like A to W, right? So let's try. So let's say we try A to W, and we will basically we assume that we have connected a wire from A to W, and then we'll see the fitness of this particular wire configuration. And if that fitness value drops, which means that we have screwed up, this particular wire configuration is most likely not the case, or not it. So we will do this for the whole text. If any time the fitness increases, then we will say that the wire configuration could possibly be correct. So we will basically do this for the whole text, for all the plain text letters that we know, the ciphertext to plain text mapping, I mean. And from there, we will roughly get about like some amount of wires, possibly not all the wires will be used. Then from the remaining wires, what we do is we do the old brute forcing way. So like let's say we already have 3 or 4 wires that we know, based on this known plain text like fitness cracking. Then we will just do a normal brute force, which is basically just start connecting wires like from here to here. For example, for the fifth wire, right, we will connect here to here, take the fitness value, save the fitness value, take this fitness value, save this fitness value, and take this fitness value, save this value, and do this for all the remaining for that particular wire, for this particular wire. And then we just take the best fitness value, and from this best fitness value we are able to determine that particular wire configuration. In fact, you don't even need to do this actually. You can just go straight to this, and you can brute force the number of wires, and that is what we did. So we actually made use of just this to brute force because we are using Rust and it's very fast. So that's basically my whole explanation on like our CTF, I'll just show you basically our Rust implementation, or like just not really our Rust implementation. You can just read up on it if you want to, because it's really there. Unless it's not there because my partner just hide it from you all, but like it's good luck then. But I will just show you that it actually runs. Thanks. Yeah, so basically you just do what I just told you, basically known plain text attack, and then cracking the rotor configuration, finding the fitness, and then you get the solution.